Hello, everyone. Thank you for attending today's webinar titled Wastewater Recovery, Applications, Treatment, and Smart Technology Solutions, brought to you by Products Finishing and presented by Xylem. I'm your moderator, Scott Francis, editor of Products Finishing. Today's presentation will last approximately 40 minutes, followed by a question and answer session. If you have a question, you can type it at any time during the webinar in the Q&A section of the chat. The webinar is being recorded and when complete will be made available to you via email from Products Finishing. We have two presenters today. Chris Riley is the Technical Services Director for Xylem's Evoqua Wastewater Ion Exchange business. He has multiple environmental engineering roles in the electroplating and environmental consulting industries, or has held those, and has worked in the areas of wastewater treatment and operations support, environmental auditing, and process waste minimization. Jeff Belote is the Senior Business Development Manager for Xylem's Evoqua Wix Group and has a history with Evoqua since 2014 with roles including the ultra-high purity water and wastewater teams. Gentlemen, I'll hand it over to you.
Thank you. Well, it's good to be here. Thank you for everybody who decided to join in. We look forward to giving this presentation. Just a quick agenda recap of what are the goals of this presentation, some of the topics for our discussion. We're going to review some of the rinse waters that are typically generated from metals finishing processes and the related processes. We're going to do a quick assessment of some of the commonly applied treatment technologies and also some of the technology sets that go into treatment. I think it's good to kind of build a framework of technology sets that fit together rather than just a technology solution all as a whole. And then we're also going to discuss some digital enhancement and how bringing a digital platform and some digital connectivity to these solutions really benefits operations. So just quick sections 1 through 5. It's going to be pretty simple today. Just a quick introduction to who we are as Xylem, now with Evoqua. And the next slide here, there we go. We're really two leaders now in the water treatment and technology space. Evoqua joined Xylem, and both Chris and I are legacy Evoqua employees. We joined Xylem earlier in 2023, and the idea behind the joining of the two was to create a transformative platform across the water service industry, where like we often say, Evoqua treats the water, and Xylem does a great job of moving the water. So combining the two just makes really good sense. We support the entire life cycle of water. So as I stated, where Xylem moves the water, they assure and deliver it, move it, and Evoqua comes in during the test and treatment phase and the monitor and measuring phase. And now combined, we can optimize and automate a lot of processes together as a large organization. We have a lot of proven expertise across this industry. Forget for a second the two people that are on this screen, both myself and Chris, who have a combined 55 years of wastewater treatment experience. We also have a whole team of people behind us who, bring many more centuries even beyond that. So really unmatched service and customer support from that angle. And finally, just as the introduction, we have a very high commitment to sustainability. Our sustainable, how we view sustainability is really the bottom line impact on health and wellness every day for our communities that we serve and for the globe. We are aligned on our product development, and we are aligned on our offering on the UN Sustainable Development Goals to create a more sustainable future for not only for us in the here and now, but for future generations to come. With that, before we get into wastewater generation review, we'd like to introduce a poll. You'll see an opportunity to respond to the poll here. We'd just like to know what industry you represent. We like tailoring these conversations to different different folks. So we'd really like to know what industry you're from, and take a moment to respond to that poll, and then we'll continue on. Chris, I'll turn it over to you.
All right, thanks, Jeff. I want to reiterate my thanks as well for everybody that's joined today's webinar. And now let's get into talking about some wastewater. Okay, the typical metal finishing, metal processing industries, there's a lot of different processes that are typically employed. And a lot of those processes, and virtually all of those processes, generate some sort of wastewater. I mean, metal finishing, metal processing is a aqueous intensive, water intensive set of processes. And so there are a number of the common processes here shown on this screen with electroplating, electroless plating, various coatings, etching, printed circuit board assembly and manufacturing. So that would account for folks that both populate boards as well as make the boards, which by that type of process, that employs a number of the other metal finishing processes, such as electroplating and electroless plating, and just various types of critical cleaning applications, coating prep, say for powder coating, where you need to do the prep, the phosphate prep. That's very water intensive, and just water used for rinsing parts of any type. It's a very water intensive industry, so there's a lot of opportunities for reuse as well as opportunities in quotes for treatment in general. So we talk about the wastewaters being generated. So what's in them? What causes the need for treatment? There's a number of different things, and the slide gives examples of the most common types of issues from wastewaters in the metal finishing and metal processing arenas. Just acidity and alkalinity, the pH is too high, it's too low. It could be something as simple as that for treatment. Other contaminants you might see would be solids, particulates that come from the parts themselves that could be generated with the chemistry's interaction with the parts. And there's also good old total dissolved solids, which is everything in there that's dissolved, anything that's ionic, for example. There could be organics. Usually those are determined as total organic carbon, which is a very general analysis that identifies what organic materials, or that there are organic materials within a wastewater, but it does not identify what organic materials are in wastewater. And that organic family is extremely huge, so that TOC can encompass a number of different compounds. You'll see regulated metals, or the typically regulated metals, such as cadmium, copper, chrome, lead, nickel, silver, zinc. You'll see typically non-regulated metals also, such as calcium, magnesium, manganese, molybdenum, sodium, potassium. These all can end up being considered contaminants that have to be removed. Also in the metal finishing industries, metal working industries, metal processing, you'll see a fair amount of hydrogen peroxide used as an oxidizer and cyanide in some of the actual electroplating type operations. So all these things may show up, some or all of these things may show up in wastewaters, and they need to be removed, plain and simple. So that's usually the goal of wastewater treatment in general. So why? Why do we want to treat wastewater and water in general? Well, there's a number of reasons. On the way into the process, typically you've got processes where water is that critical component. You need very clean water or high quality water to have effective rinsing of the parts in various metal finishing processes and other types of processes. So you need to treat the water on the way into the process. Well water, city water can be fine for many processes, but those waters themselves can contain contaminants, if you will, that need to be removed prior to being used in a process, because you're trying to protect parts from spotting or other types of quality control issues, and you're trying to protect the process baths themselves from contamination that could be caused from water background components. You may also have quality requirements that are set by, say, an industry standard, whether you be NADCAP certified, or you have some mil-spec processes, you have some ASTM requirements for your water quality. So there's a number of reasons why you need to have the high quality water on the front end before it even becomes wastewater. Now, on the backside, on the way out of the process, you have your wastewater. Why do you need to treat it? Well, first reason typically is environmental compliance. You're just trying to comply with any state, local, federal regulations that you need to so that you can compliantly discharge that water. Then you have recovery and reuse. It's like, okay, we're making this water, we're gonna discharge it. What's the possibility we might be able to reuse that? And why would I want to do that? Well, you can capture that water and use it again, perhaps in the same process it came from, or you might be able to reuse it somewhere else in your plant. From that, you're able to hopefully minimize your wastewater discharge, as well as minimize your water consumption. Jeff, I think we had another poll at this point.
That's correct. That's correct. So the second poll here, before we move into some of reuse treatment goals and what those look like, we want to know what your reuse treatment goals are. Just some options that are there. Maybe pick the best one for you, but we'd be interested in your responses. Okay, back to you, Chris.
Okay, thanks, Jeff. Appreciate it. All right, so you're thinking about wastewater recovery, and should you even do it? What are some of the things you need to think about? Sometimes it's quite simple, and other times it can be very complex, but you have to go through a number of different thought processes just to make sure that it is even something that you want to do, because it always sounds good. Sometimes when you get into the nuts and bolts of it, it can end up being more complex. One of the first things you want to do is just try to understand, why do you want to recover water? What are your goals going to be? Are you trying to improve your sustainability profile? Just cut down on your wastewater discharge. Perhaps your facility or your company has master sustainability goals that you'd like to be a part of, or that you need to be a part of. You could have other issues, say with local water supplies. You may need to recover some water so that you can make room for process expansion if you have, say, some water consumption restrictions, either back end or front end for your processes. So you really want to understand, okay, why do we want to do this? What's the reasoning behind it? Have to think of the compliance considerations as well. What do I mean by that? Well, if you take a wastewater and you remove it from your overall wastewater stream, there can be potentially positive impacts, or it can be potentially negative impacts. So you have to understand what removing a particular stream is going to do for you. For example, if you have one stream that has cadmium in it, you can remove that stream by reusing it, for example, from your overall wastewater stream. You can't be out on cadmium if there's no cadmium from that stream in your wastewater. So that could be a positive. On the negative side, if you remove certain wastewater streams, there may be other contaminants in your overall wastewater stream that will become a little more concentrated. So you have to be cognizant of what impact you will have on your compliance by removing one or more wastewater streams. To think of some operational considerations as well. Again, what's the impact of the recovered water on the particular process that you want to send it to? Many times, on the smaller reuse type systems that we see, the reused water is going directly back into the process from which it came. A lot of times that is certainly the safest play, as if you do have any leakage of any contaminants, typically they're going to be in that rinse anyway, so there's usually no detriment to, say, any following baths through drag out of any particular contaminants. But you have to understand what the impact may be on the process where you're going to send any recovered water. Think about the manpower requirements. Are we going to have additional folks needed to look over the systems? Are we going to have a lesser need for manpower requirements? It's a good time to think about that as well. And then the big thing too would be when you have multiple streams that you might want to consider for reuse. Do you want to look at point of use type systems, or do you want to look at a centralized system? There's some things that go into that, which we'll cover on the next slide. But that is one thing or another thing you want to think about. Do I want to go with one big system or several smaller systems? or a combination of both. And of course, there's cost considerations, capital costs versus operational costs. Some of the systems that we'll talk about here are going to be heavier on the capital cost side and lesser on the operational cost side, and some will be the opposite to that. So there's a few things you want to think about: your goals, compliance considerations, operational considerations, as well as cost considerations. All right, so now you've thought about it, you want to look into water reuse or recovering some wastewater for reuse. So now how do you proceed? Well, we'll start back again. We're looking at the goals, identifying the drivers and constraints that you may have. You know, what are your priorities? Do you have those restrictions or things, capital costs versus operating costs? Do you have one versus the other in abundance, or do you have both available? And here's where you may look back at your corporate, or facility sustainability objectives and say, okay, this is what we want to do. We generate or we discharge X amount of water. We want to hit a reuse goal of 25%, 50%, whatever the number happens to be. So with those goals in mind, then you kind of want to look ahead and say, we can recover water. Where can we use it? Just because we can recover water, it may not be usable in all the spots that you might want to within your facility. So you have to think about which processes might this recovered water go to. Like I said, does it go right back to the process that generated it, or does it go somewhere else within the plant, cooling tower, for example? What are the water quality requirements for those processes? What water volumes and flow rates are required for those applications? So you want to understand those things before you get into more characterization of your wastewater to determine, where it's going to go. You want to say, okay, where is it going to go? How can we use it? What quality of water do we need? Then you're going to look at your existing wastewater streams. What processes generate wastewater? It's like doing a water audit of your facility. Where does the water go in? Where does the water come out? What are the volumes and flow rates of the different wastewater streams? Are they commingled at the moment? Are they segregated? Can they be segregated? When we talk about treatment, usually if you're looking at a segregated waste stream for treatment, you're looking at a simpler waste stream for treatment than when you commingle. Not always the case, but in many cases that is true. So you want to understand what existing wastewater streams do I have, and how much of them do I have, and how easy would it be to segregate if that is the way I need to go. So you identified the waste streams, now you want to characterize them. So you have to understand, okay, I know how much, I know from where they come, so what's in them? What are the constituents? What's the background chemistry? Not just the contaminants that come from parts, for example, but what are the contaminants that come from the background chemistry as well? Are there any commonalities between different wastewaters? Can I potentially combine similar types of waste streams to make easier treatment, or to make a one system versus several systems? Might any of the constituents be problematic? Either for certain processes that the recovered water is going back to. Is there a risk if, for example, if you had some of these contaminants that may leak through, what would they do to those downstream processes? You want to minimize that risk. You also want to understand, as I mentioned on the previous slide, what happens from a compliance standpoint. Should I remove certain wastewaters from that stream? What is the impact on the stream that is remaining? So now you know the waste streams, you know what they look like, you know what's in them. Now you want to develop the solutions. So you go through a technology review. What technologies are appropriate? Am I looking at point of use recovery, or do I want to do a combined system, or do I want to have both? Do I need to do some bench or pilot scale testing? If so, what does that involve? What is the footprint going to look like? What are the anticipated maintenance needs, manpower needs? Ultimately, you're getting toward the cost, right? And then you're looking at what level of controls, alarms, how might this system integrate with, say, a building management system? Once you've identified your solution, you've got it installed, the work doesn't end there. You've implemented the solution. Now you're looking at, you go back and review First off, is it meeting expectations? Second off, if it isn't, or even if it is, how can I optimize that? Can I continue to tweak it to make it better and better? If I do need to expand that, am I able to do that easily? So there's some things to think about. All right, so we talked about the should I do it, how would I go about doing it, or what's the process to start doing it. Now we'll talk about some of the actual treatment and recovery technologies. There's really several, I'll call it common technologies that are used. There are other technologies certainly that are available. We're going to cover the more common ones that we see out there for metal finishing type rinse waters and dilute wastewaters. So the type of treatment options that exist, you've got ion exchange resins, tried and true, been around for decades and decades. Used to remove metals are general total dissolved solids, from the solutions. You've got carbon filtration, used to remove organics. In other words, things that are measured by that total organic carbon or TOC type test. That's where carbon comes in. They have reverse osmosis, which is used for TDS removal. Various types of filtration technologies that can be used, and ultraviolet light, of course, can also be used when it comes to TOC or bacterial control. So we'll talk about each of these in a little bit more depth here. Start with ion exchange and carbon adsorption. These are very commonly used in the metal finishing, metal processing industries on wastewaters for recovery. Ion exchange resin is just a functionalized plastic bead, essentially. What it does is it will attract a contaminant. In this case, we're showing copper sulfate, for example, entering a couple of different ion exchange resins. It'll attract the copper and spit out hydrogen in its place, the cation resin component of that will. That water then moves on to the anion resin, where it takes out the sulfate and replaces that in the water stream with hydroxide. Hydrogen and hydroxide together just make water, so that's how you get pure water from a wastewater stream. It's a rather simple process. IX will remove dissolved ionic contaminants, or TDS. It doesn't do much, or I shouldn't say it doesn't do much for particulate. You don't typically want it to be taking out particulates. It can remove metals and other contaminants to ppb levels. And deionizing resins can produce quite pure water for reuse. Carbon adsorption is usually something that is used in conjunction with ion exchange resin, or it could be used as a standalone treatment process as well, depending on your quality requirements for the recovered water. Carbon adsorption uses granular activated carbon, commonly known as GAC. That particular media is used to remove organic components, again, measured by the TOC, or total organic carbon. Now, one thing about carbon, in the metal processing, metal finishing areas, most of the chemistry, virtually all the chemistry, is extremely water soluble. So carbon has its limits on things it can remove. Carbon loves to remove things that are not as water soluble and that are larger. So if you have smaller, quite water soluble, like some of the simple alcohols, carbon's not going to really remove much at all. So you have to understand the limitations of carbon when it comes to organic removal. We'll also reduce oxidation compounds, chlorine, prechlorine, as well as hydrogen peroxide, and it can provide some clarification. You prefer it didn't. Hopefully we'll get into, hopefully we'll be using filtration for solids removal and clarification, but carbon can also provide another level of that. Reverse osmosis is a commonly used technology when it comes to water recovery. RO, reverse osmosis, it uses a polymeric membrane to separate. You hear people talk about osmosis. And what is osmosis? Osmosis is when you have two dissimilar solutions separated by a membrane. The water wants to flow from the dilute portion into the concentrated portion to make the concentrations equal. In reverse osmosis, you're just reversing that type of process. You're using pressure on the water to essentially shove the water through that water permeable membrane, retaining most of the dissolved solids in a more concentrated stream. Membrane pore sizes are extremely small, so you can remove much of your TDS, over 95% or above, typically with an RO. It has good rejection for TOC, silica, bacteria. What you end up with, of course, with RO is a clean stream. Could be called a permeate, could be called a product. You may end up in the single-digit microsiemen for conductivity. So it's a decently clean stream that you could use directly or further polish, for example. And you'll end up with what we call a dirty stream. Could be called a reject, could be called a concentrate. That's where everything that didn't go through the membrane stays in that concentrated stream. A couple more filtration type technologies. Microfiltration really is used more as a solid separation step to replace a clarifier in a lot of conventional type precipitation systems. So you may see a microfilter preceding an RO, which then could precede an ion exchange type system. So you could see a microfilter in that vein for larger solid separation. On the other smaller sized solids, you could see ultrafilters used. Can remove turbidity, particulates, bacteria, pathogens. You see ultrafilters more so on the potable water side, but you will see them engaged in some wastewater treatment applications as well. Not quite as tight as RO, but not as loose as microfiltration. Mentioned filtration or particle filtration earlier. That again is usually used in conjunction with one or more of these other technologies. Filtration, whether it's bags, cartridges, or media such as a sand filter or other type of media filter, those can be used as a standalone step. They can be pre or post-treatment, say, for some of the other technologies we've talked about, and they're all there to remove solid particulate contaminants. You don't necessarily want solids to get into your RO system to follow the membrane. You don't want solids to get into your ion exchange resin, because they have the annoying habit of making their way through the resin, or they can plug the resin as well and cause flow issues. Ultraviolet light's another technology used in reuse applications. When you have water going round and round and round, and perhaps you don't have as much bleed as you might need, you can get buildup of things. You can get the potential for bacterial growth. You can have TOC that can potentially build up, because I mentioned before, the carbon's not going to necessarily take out all that TOC. Ultraviolet light can be employed to knock out some of that TOC, depending on what wavelength you use, or it could be used for removal or reduction of microbial activity. Usually when you are using a UV, you're going to follow it with some sort of submicron filter to remove, say you're using it to kill the bugs, you got to have a filter to get the dead bugs out of there. So UV light filtration, a lot of times used in combination, can be used as standalones, always usually part of a larger type of reuse system employing, say, resins and or membranes such as RO. So you're looking at some initial vetting of different types of technologies where they might be employed. There's various rules of thumb from the diagram there or from the chart. If you're talking high volumes, high amounts of impurities, metals in this case, an equipment solution is typically going to be your best bet versus a media solution. Doesn't mean a media solution won't work. It just means that media solution may be much more expensive to operate. When you're looking at low concentrations, more dilute solutions, a lot of times the media solution, ion exchange resin, absorptive media can be your better option. When you're looking at pH and total suspended solids, equipment is the way to go. We've tried to use media. I know when I talk media, I'm talking ion exchange resin or carbon, something like that. You can try to use that to balance pH and try to use that for total suspended solids. Not the best idea. You're usually going to go with an equipment solution at that point. When you're looking at media versus equipment, usually with the media solutions, you're talking a lower need for attention, lower capital cost, and typically a smaller footprint. In the end, you may end up, and you likely will in a number of cases, end up using a combination of these technologies. Just a couple quick, very simple diagrams on how things might be used. In this case, it's ion exchange treatment. You'll have ion exchange used on the front end to provide clean water to your, in this case, wash bath and the following rinse. And you'll use a wastewater ion exchange system to recover that water and send it right back to that same process. And I show a discharge stream, and that's usually a bleed stream, because I mentioned there's some things that will have a tendency to build up in a recovered water stream, and one way to mitigate that is to do a regular bleed and just discharge some of that water. You can use RO, as I mentioned before. You can generate a product clean stream and a reject dirty stream. So once again, you've got that makeup water DI system on the front end to give you clean water to start and to use for makeup water. The RO is generating those two streams. The reject potentially could go straight to discharge, or in and of itself could potentially go to another operation within your facility, say a cooling tower. It all depends what kind of contaminants are in there and at what levels. Or if it is some sort of regulated contaminant that needs to be treated before discharge, that reject then could go through a wastewater ion exchange type system. Let's talk a little bit about digital enhancement of wastewater ion exchange. We'll start just by talking about wastewater ion exchange in general. Take a little bit of a step back. Wastewater ion exchange service, what is that? In wastewater ion exchange service, typically you're using portable ion exchange vessels holding ion exchange resin or adsorptive media, and you're just using that media to treat an inorganic wastewater. You're trying to get the contaminants out onto the resin so that you can send that water stream on. In this case, for the purposes of our discussion, send that water stream on back for reuse in whatever process is destined for. So in a wastewater ion exchange service scenario, you've got service-based lease tanks. The tanks get used. When they're done, the tank itself is exchanged. Tank goes off-site to a centralized facility for processing. That's a way to minimize system footprint, minimize maintenance, minimize on-site chemicals. Since you're not doing the regeneration on-site, you have no need to have those necessary chemicals and equipment to do that regeneration. So you're eliminating that on-site handling. The media goes back to a centralized permitted facility that can handle whatever you send to it from a hazardous or non-hazardous type scenario when it comes to your spent media. That facility then will also recover any metals that come off of that spent media. So ultimately, that resin doesn't end up in a landfill somewhere, or the residuals from regeneration of that resin does not end up in a landfill somewhere. And typically you'll have technical support, treatability testing, media profiling, and transport behind you as well. So that's kind of the wastewater ion exchange service, the basics about it. So what's this enhancement we're talking about? Well, it's something called Water One WX services, where we're taking wastewater ion exchange services, adding a remote monitoring and data logging capability onto systems that are being used to treat wastewater for reuse and or recovery. Those wastewaters typically at the moment will be non-hazardous, lower TDS industrial wastewaters, but it doesn't mean other wastewaters couldn't be used for this as well. So what does this service provide? What's it sets it apart from regular wastewater ion exchange? Well, it's that monitoring and data logging capability where you have that consistent recovered water quality for your process. Why? Because somebody's watching it. Big Brother is watching it. You've got 24/7 remote monitoring of the water quality coming off of that system. When the quality is not what it needs to be, or a tank needs to be exchanged, system alerts come out for that, as well as say leaks and filter obstructions, and alert folks that they need to make those types of changes, whether it's a tank change, filter change, or what. So a way to streamline the system operation and to allow you to have less interaction or attention to your water treatment system. From the data logging, we've got performance and predictive data analytics that come out of this system, and you're able to look at water quality reports. That can be important if you happen to be subject to audits by your customers, for example, if you're NADCAP certified. There's automated proactive service that comes from this. You don't have to determine when a tank is spent. It's automatically determined, and an automatic tank change is enabled as part of this service. How does it work? Well, there's a small skid that attaches to your wastewater ion exchange system. That skid does the measurement, does the logging associated with your recycle system. That information is sent via a link to site technology or a communications portal to Xylem's digital command center, where folks are actively monitoring the wastewater or the water quality that comes out of your wastewater recovery system. It is this digital command center, or DCC, that actually initiates the mixed bed tank changes. When tank change is needed, the DCC notifies the respective branch, Xylem service branch that's in your area, who then schedules and carries out that required tank exchange. So in a nutshell, that's how that service works. What kind of things does this skid measure and log? Well, there's a number of different parameters. There's an example on that slide of a dashboard from one application. The skid will constantly or continuously measure and log wastewater feed connectivity. What's the water going into the system? The effluent resistivity coming out of both ion exchange beds. Wastewater temperature to look at differential pressures across the pre-filter and also measure the wastewater volume processed. So it's measuring a number of things. It's also then calculating a number of things that are used for various algorithms. It'll calculate the average flow rate, the average wastewater feed connectivity, the estimated remaining capacity. So what it's doing is it's monitoring, it's measuring, it's predicting. For example, okay, how much longer does that worker mixed bed tank have before it needs to be exchanged? And it's also keeping that data such that reports can be generated from this particular tank or previous tank changes before it. So it's a means to access a lot of water quality data, real time as well as historical. So we've got a little example here, and we're going to talk, or Jeff will talk about this.
Yeah. At this particular site was particularly challenged with treatment efficiencies and being able to maintain high uptime, meaning that they were constantly running around from place to place. It might sound familiar to you. They didn't really have as much time to pay attention to the water system as they particularly like. And, in this instance where it's ion exchange, it's a pretty simple, straightforward, is the water quality good enough or is it not? And that's what generated the need for an exchange of this. Well, when we can provide a solution to come in and say, well, let's take that on a digital platform and substitute this ion exchange or augment this ion exchange system with a digital data collection system that's remotely monitored and worked extremely well. The customer was able to monitor several data points. It also did all of the above of what Chris was just talking about. They had the opportunity for them to look at water quality data on the outside, the data logging feature that goes behind it for their audits, as well as being able to trend historical data to see if there were any major faults or any major issues with the system. And actually, it did represent one that's on the next slide here. Pretty interesting. You'll see it. First, just to give you a little bit of context of what you're looking at here on this graph, and this is something that the data analytics are provided back to the customer as well as the service provider. In the red sections showing here are flow status, meaning that flow is on. So that's the periods of time where we care about the input and output of the water quality. On the next section here, these are the feed water conductivity spikes. So why this is interesting is that you can see over the course of just a 3-day period of time in this particular snapshot, very specific time of the day when feed water conductivity elevates. And that was a direct result of site operations who were supposed to meter in cleaning chemical throughout the day per their SOP, but it happened all at once, right? So something that where the SOP wasn't necessarily being followed, but the data doesn't lie. It doesn't you know doesn't necessarily care about what's going on in the background. It just gives you an opportunity to look at this and say, well, there's something going on at this same point of time every single day. And in this in particular instance, it was because the spike in conductivity was a direct result of cleaning chemicals being added at a certain time each day all at once when they were supposed to be metered in over the course of the day. Because of this, operational changes could be made from the customer's standpoint, and they could even that out. But something that where you're able to see this from a very just picture worth 1,000 words type view. And if you go to the next slide, Chris, just to recap it there. Oh well, sorry. But what is key here is that you're able to look at all these data parameters and be able to see going forward what those spikes look like, what some of the flow status is, and then also in the green and in the orange, you see where it says polisher resistivity and worker resistivity. What that translates into is actually the bed life and the bed capacity. Is the deionization beds, are they surviving or are they starting to crash? When the system is off, obviously it's a condition you're not concerned about, but when the system is on, are they performing to the desired effect that they should be? And this answer was yes, but it gave a lot of data all in one point. But if you start to parse it out, you're able to look at something where you can see operational efficiencies can be made just by having the data handy to you, in a very short period of time. This didn't take long. I think we were running for 2 weeks by the time we had developed this data set. Chris, I'll turn it back over to you for the summary.
Yeah, thanks, Jeff. And just a couple of things I would add to that as well. And this illustrates the ability to affect troubleshooting operations, before there's an issue. If we can see certain patterns in either effluent quality or influent quality that could potentially lead to trouble or cause tanks to be exhausted quicker than we would expect them to be. Having the availability of this data is very helpful to us, and it's helpful to our customers as well. Obviously, they can be assured. They can not only be assured of their water quality, but they can have the reports to show it should it be asked for by one of their customers, say. All right, so in summary, we've talked about a number of things here. On the metal finishing arena and metal processing type operations, they can produce a number of different wastewaters. And a lot of those wastewaters actually are ripe for recovery. A lot of rinse water, a lot of low TDS wastewaters are generated from those types of processes. And those are typically better targets for recovery. And if you're talking equipment versus media, for example, RO versus ion exchange, a lot of that's just driven by mass times volume. How much stuff do you need to take out in what time frame? And that can drive you toward which technology might make sense. And of course, technologies can certainly be mixed and matched and are mixed and matched all the time, to arrive at the desired solution. There are a number of things to consider when you're contemplating wastewater recovery. You're thinking about sustainability, impact to your operations, impact to your compliance, and of course, ultimately, what's this going to cost? One thing, we should mention, if water recovery is strictly governed by, I want to save money on my water bill, and if that's the only type of parameter that you're looking at, water recovery may not be the thing. There's a lot that goes into it, but you have to consider these other things, not just impact on my incoming water bill, for example. There's several technologies or unit operations, that exist. There's a number of common ones that are used. I talked about ion exchange and reverse osmosis because they're the most common ones. Types of technologies you're going to see in dilute, rinse water recovery, along with filtration, carbon treatment as typical adjunct treatments that go into that overall treatment system. And you can add value to an ion exchange system, for example, here with this digital connectivity on a recovery system, that the remote monitoring, having the automatic tank changes triggered, can take your attention away from the system and get your attention on other things that are typically popping up everywhere in a production plant. And having that real-time data, having that historical water quality data can be useful to optimize the operation, enhance troubleshooting, and to help your customers, should they audit you, be convinced also that the water quality portion of your process is certainly up to snuff. And with that, I want to thank you for joining us today. Contact information is on that slide, and I think we'll open it up to any questions.
Awesome. Thank you both. Again, if you have a question, please enter it in the Q&A section of the chat. And just a reminder, the webinar is being recorded, and when complete will be made available to you by email from Products Finishing. First question, does this work for sulfur removal and organics?
The actual recovery technology, or I guess let's start with that. As far as organics, again, that's a large realm, so it really depends on what the organics are. There's certainly technologies out there for the removal of a lot of the water-soluble organics, many of the solvent-type organics, for example, activated carbon, other types of media are good for that. If you are talking the digital connectivity, the digital recovery technology, that would be available to any type of recovery stream, but you would be measuring, again, resistivity, conductivity, things of that nature. It wouldn't measure any specific contaminant. I hope I answered that to your satisfaction.
If a semiconductor facility uses electrocoagulation to remove EDTA from wastewater, what should be the next step? Additional filtration?
On the recovered water, if you're removing EDTA, and you actually, in general, if you're using electrocoagulation, you're going to want some sort of filtration after that to ensure that anything that has coagulated, fallen out of solution, is removed successfully. And that could be, depending on how much is there, that could be a number of different types of technologies. That could be anything from a microfilter down to a cartridge filter, but filtration would definitely be your next step. Then if you're going to look further, once you have the solids out, okay, now what's left in there from a TDS, dissolved solid standpoint, and what technologies do I need to remove that?
I think this is a follow-up. Is there a better alternative to electrocoagulation for facility discharging EDTA?
EDTA is a tough one. Depending on how much is there, you could potentially remove it via ion exchange. I've seen that in cases of dilute type applications, since EDTA, or the salt of the EDTA, is typically ionized. There would be, this would be going the other end of the spectrum. On the expense side would be types of oxidation or advanced oxidation type processes.
Okay. Sodium nitrate liquid solutions used in electrochemical machining industry, and molybdenum ions dissolve in the sodium nitrate liquid solutions as a byproduct. Is there a method to remove only molybdenum from the solution without affecting sodium nitrate level?
It's tough because you've got nitrate and you've got moly, which is typically, or molybdenum, which is typically exists as an anion in solution. It'd be tough to remove one without the other. The one way, potentially, it would be the selectivity difference between molybdenum, assuming it is molybdate, for example, which would be a -2 type of anion, versus nitrate, which is a -1. If you've got similar concentrations, you could probably remove moly, but I suspect from the way this is described that the nitrate is much higher than the moly, and that would be a difficult thing to remove.
Is there a
I think there are some electrochemical type processes that are out there. I've not used one specifically, but I've read about some that may be helpful in a case like that.
Is there a general standard conductivity that rinse water should be?
It really depends on your process. You're cleaning a circuit board, for example. You're trying to get every last little bit of anything off that board to get it as clean as possible. So you want extremely low conductivity or a very high resistivity for your rinse water. If you're looking at a powder coat pretreatment type process, you can get away with city water quality, for example, 200-300 microsiemens type conductivity for that type of process. So it's really process specific when it comes to what conductivity is best for your process. And as a corollary to that, cleanest isn't always the best either. The more you take out of water, the higher quality water you make. That water can actually end up being corrosive to some metals. So you have to understand what are you processing and what are the limits of that process. So I'm sorry I can't give you a direct answer. It really is process specific.
Okay. That's probably time for a good reminder that if there's additional questions on this, you can the presenters can reach out to you and just kind of clarify what you're really trying to dig into. So
absolutely.
So if there's an aspect of this that can be taken offline. Next question. In our rinse systems, we have residual coming from electrolysis nickel that have huge quantities of ammonia. Is that a problem?
It can be. Ammonia is a mild complexer, so ammonia will have the tendency to tie up metals, and electrolysis nickel, of course, it can tie up the nickel. So it depends on concentrations, depends on the tolerance of your system, your rinse or your rinse water itself, the tolerance for that ammonia. Ammonia removal can be a little tougher because it is a smaller ion. It is a single monovalent ion. It's a well, when it's ionic, I should say, ammonia itself, NH3 is not ionic, but it changes in water to ammonium, and that's typically how it's removed ionically. But ammonia removal itself can be a little dicier, but there are media out there that can be used for ammonia removal. Their effectiveness will depend on what else is in there along with the ammonia. So yeah, the ammonia can be a problem process-wise. It can be a problem waste treatment-wise as well, especially if you're trying to do precipitation technology.
You reviewed a number of technologies for wastewater treatment and recovery. How do I choose the most effective technology for my application?
Well, it comes down to looking at that particular application. What is the wastewater you're trying to recover? What quality of water do you need out of this recovery process? And then again, what is in the wastewater itself? So a lot of times the concentration times volume of the wastewater, how much stuff is in there and how much you're generating, that's going to point you toward one technology or another. Again, something that's pretty low concentration, low volume, or even medium to higher volume, an ion exchange type system might be your better bet. If you're looking at things that are more concentrated, reverse osmosis might be your better bet. Then again, with a reverse osmosis, then you are dealing with the concentrate stream as well. But it does come down to that mass times volume to point you. Dilute, solutions, a lot of times ion exchange is your way to go. Once you start to get a little more concentrated, membrane type solutions or other, even precipitation type solutions, if it's that high, would be your way to go.
For the wastewater ion exchange digital solution, what kind of data is available and what benefit does it provide?
The type of data that would come out, say, real-time data as well as historical would be what was the average feed conductivity feeding the system, and what were the effluent resistivities coming out of the 2 ion exchange treatment tanks. What was the wastewater temperature? You might not think that's a very important piece of information, but it can be important depending on how your system is constructed. So that's, I'll call that more the real-time as well as historical data. From that data, then you can get how has each ion exchange tank performed historically, leading up to whatever's in there now. And that can be helpful from the standpoint of, am I getting the value I should out of these tanks? Am I getting the use that I should? If I'm not, based on this historical data, what's happening? Is it a feed water issue? Is it a resin issue? It can point you in that type of direction. So it can give you that assurance. Say a customer comes in and says, we want to understand this particular process of yours. It calls for X quality. We want to understand that your system achieves X quality, and this type of data could show that as well. And I mentioned before as well, troubleshooting. If you are seeing some issues or having some problems, it gives visibility to what the feed water looks like. Because when you're talking ion exchange and there's issues, there's the old adage, 99% of the time it's not the resin. And I've found that to be true in my 3 decades of working with ion exchange. But this then technology can give you visibility to what that feed water was looking like, and if there might be an issue there.
Probably have time for one more question. How does the digital control panel address if the water is good enough quality to use at the front end?
Well, when you set it up to alarm at a certain quality. In other words, if you need 2 megohm for your feed water, you would set up the alarms coming off the tanks perhaps at 2 megohms, although maybe you wouldn't want to set it at 2 just because you'd always want to be at 2, so you might set your alarm a little higher. You'd enter a set point for each tank such that when the water quality reaches that set point, it sends an alarm. And from that alarm, we determine, okay, that tank's ready to be changed. Then a tank change is initiated. So really, you end up setting that set point for the resistivity for the water going back to your system to ensure that it is always at, where it needs to be. It's also a reason you use 2 ion exchange tanks, or lead lag, or worker polisher, however you call that, so that second tank is always getting the water to where you need it to be, and you're really keeping your eye on that first tank and changing that out at a certain set point, because you don't want that second tank to ever get to the point where it's passing bad water.
Well, Jeff and Chris, thank you so much for your time today. Really appreciate all this great information.
Absolutely. My pleasure, Jeff.
Thank you so much. Much appreciated.
Yeah,
and we'd also like to take this opportunity to thank attendees for taking the time to join us today. We really appreciate you being here, and I hope you'll join us for the next Products Finishing webinar. For more information, please visit pfonline.com/webinars. And everyone have a great day. Thanks so much.
Thank you again. Have a great day, folks.